March 3, 1945, 18,000 feet above Rhein, Germany. Flight Lieutenant Pierre Klosterman pressed his oxygen mask tighter against his face as the Napier Sabre engine in his Hawker Tempest V roared at maximum power. The supercharger screamed through 24 cylinders arranged in an H pattern, each combustion stroke vibrating through the control column into his gloved hands. His airspeed indicator needle climbed past 420 miles per hour. Two Focke-Wulf 190D9s, the Luftwaffe's latest long-nosed Dora fighters, were diving on him from 20,000 feet, closing at a combined speed exceeding 850 miles per hour. Klosterman had perhaps 8 seconds before 20mm cannon rounds would begin shredding his aircraft. Every manual, every briefing, every survival instinct told him to dive. The Tempest weighed 11,500 pounds, heavier than a P-47 Thunderbolt, nearly double the weight of a Spitfire. At 420 miles per hour, the aerodynamic forces on the control surfaces should have been immense, the ailerons virtually immovable. Standard doctrine was clear: big fighters ran, small fighters turned. Klosterman banked hard right anyway. His forearm muscles tensed as he rolled the control column. The response came instantly, the aircraft snapping into a 6G turn that crushed him into his seat. The Tempest's 41-foot wingspan carved through the frozen air, the turn radius impossibly tight for an aircraft traveling at 7 miles per minute. Above him, the two German pilots saw what appeared to be suicide: a massive British fighter attempting sustained turning combat at a speed where control surfaces should lock solid. The lead FW-190 pilot pulled hard, attempting to cut inside Klosterman's turn. At 380 miles per hour, his ailerons began to stiffen. The air pressure against the control surfaces generated forces exceeding 80 pounds. He gripped the stick with both hands, veins bulging in his forearms, but the aircraft responded sluggishly. The Tempest continued its turn, maintaining full control authority. The German pilot's aircraft couldn't follow. Klosterman reversed left, the Tempest rolling with fingertip pressure. His gun sights settled on the FW-190's engine cowling. A 2-second burst from 420mm Hispano cannons ended the engagement. Inside Klosterman's wings, invisible to the pilot and unknown to German intelligence, a mechanism weighing less than 5 pounds was rewriting the fundamental rules of high-speed aerial combat. The laws of physics hadn't changed, but someone had found a way to work within them that no one else had understood. The crisis no one was solving. Between January 1943 and March 1944, RAF Fighter Command's Operational Research Section logged 127 separate incidents of pilots unable to maneuver during combat engagements above 350 miles per hour. The reports followed a consistent pattern. Pilot attempted evasive action at high speed, controls became impossibly heavy, aircraft continued in straight line or gentle curve while enemy fighters maneuvered freely. 43 pilots died in these incidents, their aircraft diving into French soil or English Channel waters with control columns locked in place by aerodynamic forces their arms couldn't overcome. Air Ministry Report AM 23443, issued in November 1943, concluded that high-speed maneuverability limitations are inherent to current airframe masses and represent fundamental physical constraints. The document, circulated to all fighter design teams, effectively declared the problem unsolvable. Heavy fighters would be fast. Light fighters would be maneuverable. No aircraft could be both at speeds exceeding 400 miles per hour. The mathematics supported this conclusion. B.S. Shenstone, chief aerodynamicist at Supermarine, calculated that aileron effectiveness decreased exponentially above 300 miles per hour as air pressure loads on control surfaces increased with the square of velocity. At 400 miles per hour, the pressure was 1.78 times greater than at 300 miles per hour. On a fighter weighing over 10,000 pounds, this translated to control forces no human pilot could reasonably apply while also managing throttle, trim, and tactical awareness during combat. Squadron leader Roland B. Mont, chief test pilot for the Hawker Typhoon program, reported controls that felt solid as concrete above 400 miles per hour. Hauptmann Heinz Bahr, a Luftwaffe ace with 220 confirmed victories, told his squadron pilots to avoid rolling maneuvers above 380 miles per hour in the FW-190. The forces required could strain control cables to failure point. Lieutenant Colonel Don Blakesley, commanding the 4th Fighter Group's P-47 Thunderbolts, instructed his pilots that high-speed rolls required two-handed yanking of the control column and were to be used only in emergencies. The accepted wisdom became doctrine across all air forces. Heavier fighters served as interceptors and bomber escorts, using speed and firepower to compensate for reduced agility. Light fighters defended airspace through maneuverability at moderate speeds. The two roles were considered mutually exclusive by physical law. Then combat reports began arriving from RAF Nuchich, home of the Tempest wing. Pilots described engaging FW-190s and BF-109s at speeds exceeding 400 miles per hour and maintaining turn rates comparable to combat at 300 miles per hour. Intelligence officers initially dismissed these reports as pilot exaggeration or misread airspeed indicators. The claims violated established aerodynamic principles. German intelligence was equally bewildered. Documents captured from the Luftwaffe's Rechlin Test Center in April 1945 included a report dated February 12, 1945, questioning how the heavy Hawker fighter achieves roll rates comparable to Bf-109G at high indicated speeds. The report noted that captured performance data showed the Tempest's wing loading and empty weight should have made high-speed maneuverability impossible. German pilots were reporting something that German engineers insisted couldn't exist. The official investigation began on April 18, 1944, at the Royal Aircraft Establishment in Farnborough. Captain Eric Brown, the establishment's chief naval test pilot and a man who would eventually fly 487 different aircraft types, received orders to determine why Tempest pilots consistently reported control characteristics that contradicted wind tunnel data and theoretical calculations. Brown had tested nearly every Allied fighter in service. He understood aileron forces, compressibility effects, and the mathematical relationship between airspeed and control authority. The Tempest's reported performance made no sense. The initial hypothesis focused on the aircraft's wing design. The Tempest featured a thin laminar flow airfoil section, similar to the P-51 Mustang's wing. Engineers theorized that reduced drag from laminar flow allowed the aircraft to maintain control effectiveness at higher speeds. Brown conducted the first series of test flights in late April, pushing a production Tempest V to 450 miles per hour in level flight. The controls remained light and responsive. He rolled the aircraft through 360 degrees in 2.4 seconds at 420 miles per hour indicated airspeed. For comparison, a Spitfire 14 required 4.1 seconds for the same maneuver at the same speed, and the pilot reported severe control stiffness. The team returned to wind tunnel testing at the National Physical Laboratory. They mounted a scale model of the Tempest's wing and aileron assembly in the high-speed wind tunnel, measuring hinge moments, the aerodynamic forces trying to deflect the aileron, at various airspeeds. The results contradicted the laminar flow theory entirely. The Tempest's ailerons actually generated higher hinge moments than a Spitfire's ailerons at equivalent speeds. According to the instruments, the Tempest should have required more force to roll, not less. The mystery deepened. Senior aerodynamicist R.J. Mitchell, nephew of Reginald Mitchell who had designed the Spitfire, proposed that wing twist characteristics explained the anomaly. Perhaps the Tempest's wing structure flexed in a way that reduced loads on the ailerons during high-speed maneuvers. The team installed strain gauges on a test aircraft's wing and conducted photographic analysis during high-speed rolls. The data showed the Tempest's wing twisted less than comparable fighters, not more. The wing's exceptional torsional rigidity should have made the control problem worse, not better. For 6 weeks, the investigation pursued increasingly exotic theories. Some engineers suggested the control cable routing somehow provided mechanical advantage. Others examined whether the aileron's mass balance affected control forces through inertial effects. Each theory led to dead ends. The Tempest's control system appeared conventional in every measurable way, yet it performed impossibly well. The breakthrough came on June 12, 1944, but not at Farnborough. H.A. Taylor, chief designer at Hawker's Langley facility, received a visit from the investigation team. They wanted to interview Sidney Camm's design staff, hoping someone remembered an unusual detail from the Tempest's development. P.W.G. Lucas, a junior engineer responsible for maintaining production blueprints, noticed the team examining aileron assembly drawings. He mentioned that the spring tab mechanism had been particularly difficult to dimension correctly on the original blueprints. Spring tab. The investigators had seen the small auxiliary surfaces on the Tempest's aileron trailing edges. They had photographed them, measured them, and dismissed them as trim devices, static adjustments to reduce control forces in cruising flight. Lucas explained they weren't trim tabs at all. The springs moved the tabs automatically during flight, responding to aerodynamic loads on the main aileron. No pilot input controlled them. They operated continuously, invisibly, at all airspeeds. The mechanism itself seemed absurdly simple. An 8-inch by 3-inch auxiliary control surface mounted on the trailing edge of each aileron, connected to the aileron hinge through a calibrated torsion spring. When air pressure forced the aileron upward against pilot input, the spring automatically deflected the tab downward. The downward moving tab generated its own aerodynamic force, pushing the main aileron back down. This aerodynamic assistance reduced the force required from the pilot's arms. Testing showed the system reduced control forces by 73% at speeds above 400 miles per hour. The entire mechanism, including mounting brackets and spring assembly, weighed 4.8 pounds per aileron. The concept originated with Leslie Frise in 1935, initially developed for light aircraft. Sidney Camm's team had refined it extensively for the Tempest, recognizing that the aircraft's high speed and heavy weight would create severe control force problems. They designed the spring tabs into every production Tempest V from the first aircraft. The system required no maintenance, no pilot awareness, no cockpit controls. It simply worked, every flight, reducing what should have been impossible control forces to manageable levels. The investigation team realized why the mystery had persisted so long. Test pilots attributed the Tempest's light controls to good design, without understanding the specific mechanism responsible. The tabs were visible on the aircraft, but their function wasn't obvious from external inspection. German intelligence had photographed Tempest ailerons in detail after examining crashed aircraft. Their reports classified the tabs as trimming devices, similar to systems on Bf-109 elevator controls. The Luftwaffe never understood they were observing an automatic load reduction system that gave RAF pilots a decisive combat advantage at high speeds. The revelation exposed a cascade of missed opportunities across multiple air forces. Focke-Wulf's design bureau had experimented with spring-assisted control tabs in 1941 during development of the FW-190's production variant. Chief designer Kurt Tank ordered the system removed after initial testing, declaring it unnecessary complexity for a fighter that would operate primarily below 350 miles per hour. Tank's engineers calculated that the 18 additional parts required for each aileron installation added potential failure points without meaningful benefit at the aircraft's intended combat speeds. The decision made sense in 1941. By 1944, when FW-190s regularly fought at speeds exceeding 400 miles per hour, reversing the decision would have required retooling production lines across 6 factories while Allied bombers systematically destroyed German industrial capacity. American fighter designers had pursued a different approach entirely. The P-51 Mustang employed boosted ailerons using mechanical advantage through a differential linkage system. North American aviation's engineers increased control throw at the pilot's stick while reducing deflection at the aileron itself, effectively trading displacement for force reduction. The system worked adequately up to 380 miles per hour but still required significant pilot effort at higher speeds. Republic's P-47 Thunderbolt used no special aileron assistance, relying instead on hydraulically boosted rudder and elevator controls. Pilots managed aileron forces through physical strength and technique. Both aircraft achieved success through different compromises, but neither solved the fundamental problem of maintaining light aileron forces across the entire speed envelope. The Tempest's advantage came from combining spring tabs with exceptionally rigid wing structure and low-friction control cable runs. Hawker's engineers had designed the wing's torsional stiffness to remain essentially constant up to 500 miles per hour, preventing the wing twist that plagued other designs. The control cables ran through ball-bearing pulleys rather than simple fairleads, reducing friction losses by 40% compared to typical installations. Spring tabs provided the aerodynamic assistance, but only because the rest of the control system transmitted that assistance efficiently to the pilot's hands. The entire system represented integrated design thinking rather than a single clever mechanism. German technical intelligence never identified this integration. Luftwaffe evaluation reports from Rechlin analyzed captured or crashed Tempest components individually. Engineers measured wing stiffness and noted it exceeded German design standards. They examined control cable routing and documented the ball-bearing pulleys. They photographed the spring tabs and recorded their dimensions. But the reports filed these observations in separate sections, never connecting them into a unified understanding of how the systems work together. The reductionist analysis method that served German engineering well in many contexts prevented recognition of the Tempest's holistic design advantage. British test pilots who flew captured German fighters after the war consistently reported the same phenomenon. Squadron leader Roland Beaumont flew a FW-190D9 at Ari Farnborough in July 1945, pushing the aircraft to 450 miles per hour in level flight. His report noted aileron forces that increased dramatically above 380 miles per hour, requiring both hands on the stick for rapid rolls. The aircraft remained controllable but demanded physical effort that would quickly exhaust a pilot during sustained combat maneuvering. Beaumont had flown Tempests operationally with No. 150 wing. The contrast was unmistakable. In the Tempest, he could maintain aggressive maneuvering indefinitely at speeds where the FW-190 became progressively more difficult to control. The psychological impact of this advantage manifested in combat loss rates. No. 3 Squadron RAF, operating Tempest Versus from Rain Airfield in March and April 1945, engaged Luftwaffe fighters on 47 separate occasions. The squadron's operational record book documented 38 confirmed aerial victories against 3 losses to enemy aircraft. Analysis of combat film and pilot reports showed that 52% of successful engagements occurred at indicated airspeeds above 400 miles per hour. German pilots attempted to disengage by diving, the traditional escape maneuver for pilots facing superior opponents. Tempest pilots followed through the dives and engaged in rolling scissors maneuvers at speeds where FW-190 and Bf-109 pilots struggled to maintain control authority. Captured Luftwaffe pilots interviewed at the Combined Services Detailed Interrogation Center between April and June 1945 revealed tactical doctrine changes implemented too late to matter. Lieutenant Franz Stigler, a FW-190D pilot from Jageschwader 26 captured on April 15, described standing orders issued in January 1945. Engage Tempests only in vertical maneuvers, never attempt sustained turning combat above 400 km per hour. Stigler stated that pilots who violated these orders often failed to return. Oberleutnant Walther Hagena from JG-54 reported similar instructions but added that many younger pilots lacked the experience to recognize when their airspeed had crossed into the danger zone. Combat occurred too quickly, with aircraft accelerating and decelerating constantly. By the time a pilot realized he was turning at 420 miles per hour with controls stiffening, the Tempest had already achieved a firing position. The spring tab system's development history revealed how easily critical innovations disappear into routine documentation. Hawker's design team implemented the tabs during the Tempest's prototype phase in 1942. The modification appeared in Engineering Change Order ECO 127, dated September 8, 1942, listed between changes to the gun camera mounting and reinforcement of the tailwheel assembly. No special emphasis marked the spring tabs as revolutionary. They were simply another refinement in a list of 347 changes made during the aircraft's development. Focke-Wulf attempted a desperate technical response in February 1945 when the extent of the Tempest's advantage became undeniable through pilot loss rates and combat film analysis. Kurt Tank authorized a crash program to retrofit servo-assisted tabs on the FW-190D12 variant, then entering production at the Tempests factory. Engineering teams worked 16-hour shifts designing a spring tab system reverse-engineered from photographs of crashed Tempest ailerons. The installation added 14 pounds to each wing and required modifications to the aileron hinge line that necessitated partial disassembly of production aircraft already on the factory floor. 12 FW-190D12s received the modified ailerons before Soviet forces overran the Tempests facility on April 19, 1945. None of the modified aircraft saw combat. The Luftwaffe's technical response came 9 months too late to influence operational outcomes. Messerschmitt pursued a parallel effort for the Me-262 jet fighter, attempting to address control stiffness that appeared above 500 miles per hour. Hydraulic boost systems added to the aileron circuit provided adequate force reduction but imposed a weight penalty of 180 pounds and required a dedicated hydraulic pump driven by the starboard engine. The Me-262's already limited endurance, fuel capacity allowed approximately 60 minutes of flight time, decreased further as the hydraulic system consumed engine power that could have driven the aircraft's fuel pumps more efficiently. 23 Me-262s received hydraulic aileron boost between March and April 1945. Pilot reports noted improved control harmony but complained that the reduced range made the modifications tactically useless. Aircraft needed additional fuel capacity to exploit the enhanced maneuverability, but no fuel capacity increases were possible within existing airframe weight limits. The statistical impact of the Tempest's spring tab advantage became quantifiable through operational research analysis conducted after the war. Between January and May 1945, 5 RAF Tempest squadrons operating from continental bases engaged in 247 documented aerial combats. These engagements resulted in 188 confirmed enemy aircraft destroyed against 19 Tempest losses to enemy action, a kill ratio of 9.9 to 1. Comparative analysis of Spitfire 14 squadrons operating in the same geographic area during the same period showed 93 victories against 29 losses, a ratio of 3.2 to 1. Both aircraft types flew similar missions against identical opposition. The Tempest's threefold advantage in exchange ratio correlated directly with combat occurring at higher average speeds where spring tabs provided decisive control authority benefits. Pierre Klosterman's personal combat record illustrated the practical application of superior high-speed maneuverability. Between September 1944 and May 1945, flying Tempest versus with No. 3 Squadron and later No. 274 Squadron, Klosterman claimed 33 aerial victories. His combat reports, preserved in the Air Historical Branch archives, consistently described engagements initiated at speeds between 380 and 450 miles per hour. Klosterman's memoir, published in 1948 as The Big Show, included detailed descriptions of combat techniques impossible in other fighters. He described rolling inverted at 420 miles per hour to track a diving FW-190, then pulling through to a vertical dive while maintaining gunsight alignment. The maneuver required continuous aileron input during speed changes from 420 miles per hour to over 500 miles per hour. Any other Allied fighter would have experienced progressive control stiffening during this speed range. The Tempest's controls remained responsive throughout. The spring tab system proved equally valuable during ground attack operations where precise control at high speed determined survival against anti-aircraft fire. Tempest squadrons conducted armed reconnaissance missions across northwestern Germany, attacking rail transport, vehicle columns, and Wehrmacht troop concentrations. Standard doctrine required aircraft to approach targets at speeds exceeding 350 miles per hour to minimize exposure to light flak, then execute rapid direction changes after weapon release to defeat tracking by heavier anti-aircraft guns. Squadron leader David Fairbanks, commanding No. 80 Squadron's operations from Focal Airfield in the Netherlands, reported that Tempest pilots could make aiming corrections during the final 3 seconds before weapon release while maintaining attack speeds of 380 miles per hour. Typhoon pilots flying parallel missions typically slowed to 320 miles per hour for comparable accuracy, increasing their vulnerability to ground fire. Loss rate statistics confirmed the advantage. Tempest squadrons lost 1.3 aircraft per 100 ground attack sorties between February and April 1945, while Typhoon squadrons lost 2.2 aircraft per 100 sorties against similar target sets. Manufacturing data revealed the spring tab system's remarkable cost-effectiveness. Hawker's production records from the Langley facility showed that spring tab installation added 14 minutes to aileron assembly time and cost £7 per aircraft in materials and labor. The complete Tempest V cost £9,500 to manufacture in 1945. The spring tabs represented 0.074% of total aircraft cost while providing the decisive combat advantage that determined victory or defeat in hundreds of high-speed engagements. No other aircraft modification in aviation history delivered comparable tactical benefit for such minimal investment. Post-war technical evaluation by neutral nations validated the spring tab system's revolutionary impact. The Swedish Air Force conducted comparative testing in August 1945, flying a captured FW-190D9 against a war-surplus Tempest V acquired through British military assistance channels. Swedish test pilots reported that the Tempest maintained superior roll rate and control harmony up to 450 miles per hour, the maximum speed reached during testing. The FW-190's aileron forces increased to approximately 3 times the Tempest's forces at speeds above 400 miles per hour.